Hello, welcome to our lesson today on design of slender columns. So in this lesson, we are going to look at how to design a column that are rather slender and not short. So these are the subheadings in which we are going to look at in this lesson. So as a matter of introduction, columns in a structure, they carry loads that comes from beam, load from slab, and they have to transfer this load down to the foundation, which could be pad footings, raft footings, or any kind of design footings. So they primarily carry compressive load, although in some certain arrangement, bending columns may also have to resist bending because of continuity and whatsoever. Now, slenderness is a critical factor in column because some columns are slender, and because of slenderness they tend to have lateral deflection, which can lead to buckling. So we need to consider the issue of slenderness when we are designing a column. So special requirements are usually applied in design of slender columns that are different from design of columns that are considered short. Now, for the purpose of column design, structural frames can be classified into the following: into brace frame and unbraced frame. So brace frame is where the lateral load is resisted by a bracing system. So in a system, maybe a high-rise building where you have the lateral loads usually come from wind or some other, or mostly from wind. So if that lateral load is being resisted by a bracing system, which could be bracing or shear walls, such that the columns do not carry resist lateral load, such frame system is considered as brace system. But we also have unbraced system where the lateral loads are not resisted by the columns, by the combination of the columns, that I call it the rigid connectivity of the frame, which is a combination of columns, beams, and slab. So if that is the system that is resisting the lateral load, we consider such as unbraced system. Now, for braced structures, axial forces and movement in the columns are caused by vertical actions, vertical permanent and variable actions only. Effect of lateral loads on structures are not considered, I've mentioned. But whereas for unbraced structure, it is the columns that help in resisting the lateral load of the system. For both braced and unbraced structures, we can further classify them into sway structure and unsway structure. Now, swaying is a sideways deflection in a column. So if the side sway is likely to significantly increase the magnitude of the bending moment in the column, we consider the structure of sway. The swaying introduced what we call second order effect, which is a moment in addition to the main moment that the column is subjected to. So if that second order effect is significant, we consider it as a sway structure. If it is not significant, we consider it as a non-sway structure. So the increase in moment due to side sway I've mentioned is called second order effect, and it is considered to be significant if it is less than 10% of the first order moment, which is the original moment on the column. So if it is less than, but if it is up to 10%, it is considered to be significant. And so substantially, brace structure are usually considered to be non-sway. So structures that are substantially braced are usually considered to be non-sway. So in this lecture, we are going to consider the design of braced non-sway slender columns. So those are you will not consider some other columns, we will only consider braced non-sway columns. So let's look about the combinations in columns. Now, for a brace structure, the critical arrangement of the ultimate load is usually the one that will cause the largest moment in the column together with the largest column. So if you look at this figure of 1, if you look at this figure 1a, if we are considering this central column, the column at the middle, this is the arrangement that will give the critical load arrangement, critical moment and critical load. So why? Because this span L1 is greater than L2. So if L1 is loaded by, you can see at the span L1 at each level is loaded by the permanent action and variable action, while the other shorter span is loaded by only permanent action. It means the load in this area will be much greater than this in this area. So the moment turn by here, the moment in this case is going to be a moment turning in this direction. So this moment will be much greater than if this other side were to be loaded with both permanent action and variable action, knowing that this right hand side, the moment here is countering the moment on the left hand side. So in the other case, when you are designing, you always come out with the most critical arrangement, that is the arrangement that will give you the largest moment in addition to the largest load. So, but if you look at this figure 1b, if we consider this left hand column, this left column, this is the critical arrangement because this column is only carrying this beam in terms of rotation. So this beam now, if the critical arrangement is when this lead is fully loaded, while in this case, the critical is when the longer beams is fully loaded and the shorter one is loaded as the minimum possible load, which is only the permanent action. So still on load combination. Now when the moment in the columns are large, and particularly with unbraced column, it may be necessary to check the case of maximum moment combined with the minimum load. So there are times you want to say, okay, what is the maximum moment that this will carry? Let's combine it with the minimum load and see the effect that it will create. Now in some structure, it is unlikely that all the floors of the building will carry their full imposed load at the same time. So therefore, reduction is allowed in the total imposed load. For instance, if you have a structure that is a school or that is an office, in most cases, all the slabs, all the structures will not be fully loaded with the imposed load at a particular time. So that is why we can have a reduction of the imposed load. For how to consider that reduction, you can look at this Eurocode BSEN 1991/1-1 Action on Structures. You get more detail on the reduction of the imposed load. Let's also know that in brace frame, the axial column load due to vertical loading may be calculated as though the beams and the slabs are simply supported, provided that the span on either side of the column differs by not more than 30%. So if for the sake of load, you could just assume that the beams are simply connected to supported by the column so that you can just calculate the loads that they impose on the column. Now let's look at the effective height of a column. The effective height of a column, which is designated as L0, is the height of a theoretical column of equivalent section but thin at both ends. So for a brace member L0, L0 is calculated as L0 is the effective length, this equation 1, which is that L0 is the square root of 1 plus K1 over 0.45 plus K1 into 1 plus K2 over 0.5 plus K2, where K1 and K2 are the relative stiffnesses at both ends of the column. And K1 and K2 can be calculated by this equation 2. That is the stiffness of the column all over the summation of the stiffness of the beam. So the stiffness of the column can be shown as EI over L, while the stiffness for beam can be 2 EI over L. Now, as we proceed, you will see why these two comes in. So if E is the same as a moment, the material, for instance, you are all concrete, So the material are the same. So E can cancel out. You now have this side of the equation. Now, it is assumed that any column above the column under consideration does not contribute anything to the rotation restraint of the joint. Take note of that. Now, the stiffness of each beam is taken as 2EI over L to allow for cracking effect in the beam. I told you I will mention you, I will show you why this 2 comes in when we are looking at the stiffness of the beam. So it's allow for cracking effect in the beam. Hence, for a typical column in a symmetrical frame with span approximately of equal length, K1 and K2 can be calculated using this equation 3. You can see. Now, these 2, where does this 2 comes in? This 2 is because you have beam at both ends of the column, beam at the top and beam at the bottom. So that gives you the stiffness, that gives you 2. Then provisional 2 that is due to cracking. So you now have this formula. 1 into L over I over L plus all over, that is for column, while this one is 4 into I over L for beam. So we can proceed. Let's look at slenderness ratio of a column. The slenderness ratio of a column bent about an axis is given by lambda. Lambda is L naught over I. L naught here is effective length. I is radius of gyration. Radius of gyration about the axis in consideration. And you know the radius of gyration is usually square root of I over A. I is moment of inertia, A is cross-sectional area. That means the slenderness can now be L naught all over square root of I over A to calculate the slenderness of a section. Now, there's what we call limiting slenderness. Limiting slenderness is a limit of slenderness which determines if a column is slender or if a compression member is considered slender or short. And Eurocode gives this formula. Lambda lim is equal to 20 A times A times B times C all over square root of n, where A is given by this equation. A is 1 all over n plus 0.25 EF. Phi EF is the effective creep ratio. Call it effective creep ratio. B is a square root of 1 plus 2 W. 1 plus 2 W. Now C is equal to 1.7 minus Rm. Rm here is, in the next page I will show you the formula. And we have seen that this is a creep ratio. W that is used to calculate B is given as AS FYD all over AC FCD. AF is a cross-sectional area of steel. FY, so this is a So NED is the design ultimate axial load. This is RM, which is the moment, the ratio of the moment at the end moment. So if usually M2 is greater than M1, the greater of the moment is M2, the smaller one is M1. That is the moment at the end of the column. So the Rm you're given by this formula. And if Rm is not known, you take C as 0.7. So we have said M1 and M2 are the first order end moment at the end. Now note, if the end moments M1 and M2, M1 and M2 give rise to tension on the same side of the column, Rm should be taken as positive. But if the column is in the state of double curvature, then Rm should be taken as negative. So that depends on the direction. If the two end moments are such that when they bend the column will now be in tension in one direction, in one side. So that is when you consider Rm to be positive. But if the moment is such that maybe the up one is clockwise and the lower one is anti-clockwise, the column will be in double curvature. You take Rm as negative in such case. Now, when we calculate the slenderness and lambda, if the actual slenderness lambda is less than the limiting slenderness, then the column can be treated as short. Otherwise, if the actual slenderness is greater than the slenderness limit, that column is considered to be a slender column. So let's look at example 1. Example 1 said the column in the figure beside is to resist an ultimate axial load of 3,500 kN and end moments of 75 kN and 5 kN, causing tension on one side about the minor axis YY. The beam at either ends are 250 mm wide and 500 mm deep, with length of 3.75 meter on each side. Determine if the column should be designed as short or slender column according to Euro Code 2. You have to take FCK, which is the characteristic strength of concrete, as 25 Newton per millimeter squared. Take grip effective group coefficient as 0.82. So this is the column. You've been given the column. This is the length. The column actual length is 5 meter, and there's a beam at both ends. This is a cross-sectional area of the column. You can see in the YY direction, the width is 300. In the ZZ direction, the height there is 250 mm. So let's look at the solution. The highest slenderness ratio of the column will be about the YY axis. That means when you're bending it among this about this axis YY, that is where you have the slenderness, and the height in that direction is 250. So let's calculate the moment of inertia for column. The moment of inertia for column in that YY axis, that is bending about this YY axis, is given as, remember, moment of inertia for a rectangular section is BH cube over 12. So this is B, which is the 300 here. This is H, which is the height 250 here, all over 12. So that gives us this value as a moment of inertia for column. Then for beam, we are told it has a width of 250 and a height, a depth of 500. So BH cube all over 12. This is the value of the moment of inertia for column. Now let's look at L for column. The actual length of column is 5 meter, which is, if you change to millimeter, because these are all in millimeter, it will now become 5 times 10 raised to power 3 millimeter. We are told that the length of the beam is 3.75 on each side. So if we change to meter, it becomes 3.75 times 10 raised to power 3 millimeter. Then the design FCD is the design concrete strength, which is, if we multiply this factor of safety 0.567 by the characteristic cylindrical strength of concrete. Once you do that, it will give you the design concrete strength. So let's calculate K1 and K2. Remember that K1 and K2 is 1 over 4 into I for column all over into I for column all over L, I all over L for column, and this one is I all over L for beam. So 1 over 4 I over L for column, I over L for beam. So that gives us K1 and K2 is 0.028. Therefore, we go to this equation. There's this equation that we use to calculate the effective length. This equation 1 for effective length. The one we just finished using is this one. So we now go now and use that equation 1 and calculate the effective length. So this is K1, this is 1 plus, this is K1 all over 0.45 plus K1, 1 plus K2 all over 0.45 plus K2. So everything we have the effective length of the column to be 1.46 meter. So we now calculate the column slenderness. The column slenderness is actually lambda L naught all over square root of I over A for column. So let's calculate area of column, the area for concrete in the column. So we just to calculate, this is the cross-sectional area 300 by 250. So that's what 300 by 250 give us 75 times 10 raised to power 3. Now, I for column, we have calculated this and we know A. So we now go to this formula. This is the effective length. This is a moment of inertia for column. This is a cross-sectional area for column. So we now give us that the column slenderness is 20.23. Note that slenderness is a unitless, it does not have a unit. So after calculating the column slenderness, we need to go and calculate the limiting slenderness. What is the limiting slenderness? Remember this formula, that limiting slender is 20A times B times C all over. And remember how to get A here, and how to get B, and how to get C. So we now go there, and this is a limiting slenderness for A is 1 all over 1 plus 0.2 phi EF, which is effective creep ratio, and we were given as 0.82. So our A is 0.86. Because we are not given W, we take B as 1.1 because it was told if you don't know, you can take as 1.1. To calculate C, we need to calculate Rm. Rm, which is the moment, the first order end moment. We were given the moment as 75 and 5. And so because we were told that the moment is at the moment is in tension in one side, that means Rm is positive, and the smaller moment is always up, the bigger moment is down. So 5 over 0.5 give us 0.07. We now go, remember C is equal to 1.7 minus Rm. So when we do that, C equals to 1.63. We now calculate for N, which is our design load all over ACFCD. Our design load we were given as 3,500 kilonewton. So if we change to newton, it becomes times 10 raised to power 3. Now AC, area of concrete, we have calculated it here to be 75 times 3 raised to 10 raised to power 3. So this is the area of concrete. Now FCD, the design strength of concrete, we have said it will be 0.567 times 25. So we put that. So that gives us N as 3.29. Therefore, the limiting slenderness ratio is given as, we now put all of them in that equation. The limiting slenderness is 17. What was our actual slenderness? It was 20. So that means our actual slenderness is lambda 20 is greater than the limiting slenderness. Then the column can only be designed as a slender column. So in this case, this column is considered as a slender column. So in our next video, we are going to look at how to design slender columns after doing all these preambles. Thank you for watching to this place. Please remember to follow this channel so that you can be getting subsequent video that will be posted. Thank you very much.